program is like this. If we say, if we have this instruction, add R3, R2 and R1. There are 3 instructions. Okay? And we are executing instruction J. We are executing instruction J. Okay. Now let's assume that the contents of R1 is 5, the contents of R2 is 3. So what value should we expect for R3? What should be the value of R3 after the execution of this instruction? 5 plus 3, 8. This should be your expected value. This should be your expected value. Now let's assume interrupt arrives here during this instruction. When interrupt arrives here, let's assume if it arrives here or here. What should we do? First, we should complete instruction J. We should complete instruction J. It can be any instruction. And let's assume the address of this instruction is $3000. Let's assume that the instruction size is 4 bytes. What is the address of the next instruction? 3004. So once we complete instruction J, which value should we store on the stack? 004. Because when the program will be resumed, it will resume the execution from which instruction? This instruction J plus 1. So this is the instruction J plus 1. During instruction J, this is different phases of instruction execution of any instruction J. Let's assume it will arise here. So first we will complete instruction J. When it's completed, control will be transferred to the interrupt subroutine. So okay. So now let's assume that this is an ISR interrupt subroutine and its address is $4000. So every control will be transferred to this interrupt subroutine. When there is last instruction RTI, return from interrupt, then okay, before jumping to this ISR, what we are pushing on the stack? Status register, program counter and working register. Why we need to push the working register on the stack? Why? I will explain this in an example. Now let's assume when before this program was interrupted, okay. So what are the working register for this instruction? So the working register are R1, R2 and R3. These are 3 working registers. Let's assume these are only 3 working registers. Once the control is transferred to the interrupt subroutine, and let's assume if it modifies the instruction, like if we say add R2, R5, R6. These are some contents. And now the R2 is modified here. Now if this ISR is modifying R2, so what will be now the new value of R2? Maybe this value is changed from 5 to 9. And when we return from this subroutine, will we get the correct value for R3 or incorrect value? Incorrect value. Why incorrect value?
Because the contents have changed.
Because the contents of the if you look at the registers are actually temporary locations. They temporarily holds the data. But when it was jumped to the ISR, so actually what you are doing, you are using now changing the contents of the register R2, and maybe this register R2, maybe okay now R2, this is 5, and maybe then it will be 9. So actually it will make the program inconsistent. The program will become inconsistent. So before jumping to the ISR, so there are 2 methods. So we also store the working registers on the stack. Okay, now which of the working register program is using? It is using R1, R2 and R3. And typically in some of the programs, what they do, they store all the working registers onto the stack. So now let's assume we have this R0, then R1, R2. Let's assume there are 31 registers. There are 31 registers. Now we also have status register. And now we also have program counter. Program counter is currently pointing to which instruction? Okay. Interrupt arrives. during the middle of this instruction, microprocessor will execute this instruction. It will store. Okay, now what is the contents of R0? So the contents of in this example, what is the contents of R1? 5. What is the contents of R2? 9. And I'm not interested in any other contents. Okay. So before jumping to the ISR, these values will push on the stack. So what will be the stack values? The stack value will be like this. So it push R0, then it push R1, then it push R2. So what is the value of R1? 5. Then 9. Then R9 is also pushed on the stack. On the top of that we have SR, status register. So maybe status register NZCV, these are the flags. NZCV, these flag values. Okay? And then it also pushed in the last of instance, it pushed the value of the program counter. And the value of the program counter which is pointing to the next instance. So actually it will push the program counter on the stack. So what is the new value of the stack program counter? So $3004. Okay, now it is the actually it may be 3004 or it may be some downward instruction, maybe 305C, maybe down. Why?
Jump.
If this instruction J is a jump instruction, if we say jump label and label has this address. Okay, so actually what it will store? It will store the address of the next instruction to be executed. This address of the next instruction can be the following instruction, or it can be a far instruction. So in case of a forward jump, now if this instruction is jump label, if you are moving to this instruction label, so we should not execute add instruction. Instead we should execute the instruction that is here. Okay, so actually what we are storing, whenever an interrupt arrives, during the middle of an instruction execution, first microprocessor will complete the current instruction. It will push all the working registers on the stack. Then it will also push the status register on the stack. We call this as the context. This is called as the context. It is called as program context. It will push these on the stack. Okay, now control will be transferred where?
Subroutine.
In direct subroutine. If it changes R2 or R3, it doesn't matter at all. When the last instruction is executed from here, in the last instruction, what will it do? The value that is on the top of the stack will be moved where? To program counter. This value will go where? Program counter. Okay, when all these values are on the stack, so actually maybe these values are changed. Maybe after this values is changed by the ISR. Maybe this is 35, maybe this is 96. Okay, so when the program is resumed, so the value that is on the top of the stack will be moved here, program counter. So now what is the value of the program counter? $3004. To which instruction it is pointing?
J plus 1.
This. And then all these values that will push on the stack, they will be restored in the working. So now after that, even if the working registers are modified by the instruction subroutine, their old values will be then resumed. What are the old values? 5 and 9. When now the program is here, it will see 5 and 9. So in this case, the program will be consistent or inconsistent?
Consistent.
Consistent. Okay, and actually, if you look at this, because you don't know at which point an interrupt will arrive. You don't know. So now there are two mechanisms. Either you push all of the working registers on the stack, okay, or you use only those working registers on the stack which are modified by ISR. Now let's assume This is one method. This is one method. Push working register and pop working register. So now how can we do it like this? So now let's assume we have an ISR. It jump to an ISR. Okay, so jump is made to an ISR. There are some, and this ISR is using R5, R6, R7 and R9. How many registers are we used by the ISR? 4 registers. So whenever you jump to the ISR, so what you do, you can code it in within the ISR. You say, okay, because I am using R5, R6, R7 and R9. So okay, what you can do? First, it will then push R5, push R6, push R7, push R. How many working registers have been saved on this stack? 4. Then there is a code for the ISR, because maybe it is using add R5 something. So it means R5 is now modified. R5 is now modified. What is now on the top of the stack? R8. So in the last instruction will be what? Pop R8. Pop what? Pop what? Pop R5 and RTI. Okay, so now what we are doing? We are using the working registers on the stack, pushing, and then and when RTI appears, so it will pop the status register and the program counter. So in this case, you are only pushing the working register, and you only need to push only those working registers which are modified by the subroutine. All of the working registers that are used by the subroutine. So there are two methods. Which method is better? Either pushing all the working register or only push that is being used by the program. It varies from architecture to architecture. Sometime in most of the architecture, let's do. Okay, this is in the case when you are executing only a single program. But what in the scenario when you are executing multiple programs? And multiple programs, let's assume if the operating system, if you are using an operating system, and operating system allocates time slots to each individual program. Operating system allocates time to slot to one program P1, then P2, then P3, then P4, and there is some scheduling mechanism that is used by the operating system. So actually the safest method, what is the safest method? Pull all the working registers. It's a safest method. Okay, it is the safest to push all the working registers. So there are different trade-offs. Different trade-offs between this alternative. Now, if you look at the switching time in this push and pop instruction, because how many instructions are there? 8. How many instructions are there? 4 plus 4, 8. So actually, first you need to push 4 registers and then pop 4 registers. Okay, how does it mechanism? Which of the mechanism will be used? Either push all of the working registers, or only push those registers which are being modified by the ISR. It depends from architecture to architecture. Okay, now we have studied that whenever a microprocessor is executing any program and an interrupt arises, because interrupt is asynchronous, it can arrive at any time. So microprocessor will first complete the current instruction. Okay. And then it will determine what is the next address. The next instruction to be executed can be the next sequential address, or it can be a forward address. Okay, the forward address can be forward jump or backward. It depends on when the microprocessor will be interrupted. Okay, if the microprocessor is interrupted during a sequential instruction, then actually the value of the program counter it will push on the stack will be the address of the next instruction. Okay? And before jumping to the subroutine, we push all of the working register on the stack, then status register on the stack, and then also program counter. And when the ISR is finished, okay, so then all of the working registers are popped from the stack, the status register is popped, and program counter is popped, and then the microprocessor will resume its normal execution. Agreed? Okay. Now, we proceed further.
सर तो लूप्स की एग्जीक्यूशन में इसका इंटरप्ट आ जाए
किसमें?
लूप्स की एग्जीक्यूशन में
It doesn't matter. Now, if you look at the loops, so how do you execute loops in the microprocessor? क्या?
काउंटर के थ्रू होता है
No, counter बात नहीं कर रहे ना. Even if you divide it into a loop, so actually we also did, you also wrote an assembly language program to find the sum of all elements of the arrays, if you remember. So in loop, what are the different parameters? You say decrement R1, compare R1 with hash 5. Okay, so these are, if you look at these loops, like how can we implement a loop? First you have to define a loop counter. Let's assume the loop counter is R10. So you initialize this value, move R10 hash 100. Now you initialize the loop counter. Okay, then you decrement the loop counter, decrement R10. Okay, then you compare R10 with some value. So if you look at the loop, these are all instructions. And instruction can be of any type. Okay, and if you remember, we have studied in our first lecture there are three types of instructions. Number one, what kind of instruction? So microprocessor broadly is categorized into three types of instruction: data transfer instruction, data transformation instruction, and then control instruction. So if you look at any instruction, it can be categorized into these three types. So now what is this instruction add? Data transformation instruction. If we say move, it is data transfer instruction. If we say jump, control instruction. Okay, now what is it? Can be a conditional jump instruction or unconditional. If this is unconditional, so it is jump instruction. If it is conditional instruction, then what is the instruction? BEQ. Now, if you say, let's assume if we have BEQ and interrupt arrives here, first it will check the condition, and based on the complete condition, okay, BEQ label. Either the condition can be true or false. If the condition is true, it will move to label. So the value that will push on the stack will be some far address. And if the condition is false, the value that will push on the stack will be next. Agreed? Okay. Any question? Okay. Now we have studied in the scenario. We have studied the scenario when there is a single interrupt. When there is a single interrupt. Now we will study this different scenario in when there are multiple interrupts. How microprocessor will handle multiple interrupts? Yes. How microprocessor will handle multiple interrupts? No. How microprocessor will handle multiple interrupts? Who will generate any interrupt from microprocessor?
IO device.
Any IO device. So IO device will generate an interrupt. So there can be a single IO device, there can be multiple IO devices. If there are multiple IO devices and multiple IO devices are connected with the microprocessor, so there are different mechanisms how to address them. The first mechanism that is used is the multiple interrupt line. Multiple interrupt lines. In this multiple interrupt line, so we say that in this scenario we have a microprocessor, and then there is IRQ1, IRQ2, IRQ3 and IRQ4. What is IRQ?
Interrupt request 1.
Interrupt request. Interrupt request is a signal which is generated by the device or by microprocessor? By the device. Interrupt request is the signal that is generated by the device to tell the microprocessor that I want some service. Okay, so it means how many devices now we have connected? 4. So 4 devices are connected. So actually each interrupt has this request. So now an interrupt, so now we also have some other signals that is generated by the microprocessor to acknowledge that I acknowledge 1, I acknowledge 2, I acknowledge 3 and I acknowledge 4. What is the advantage of this interrupt? What is the advantage of this interrupt? जी.
सर इसके पास मल्टीपल इंटरप्ट्स आएंगे तो जिसको प्रायोरिटी वो देना चाहता है उसको
No, so microprocessor will exactly know which devices has generated an interrupt. So now let's assume if this is 1 and this is 1, let's assume it is active high and 0 and 0. What does it imply? Which of the devices generated an interrupt?
2 and 4.
2 and 4 generated an interrupt. But microprocessor can service only one of them at a time.
Yes, sir.
So there can be some priorities. Some priorities. So how does it determine? So it knows. Okay. Now for each interrupt there will be an interrupt subroutine. So how many interrupt subroutine do we need here?
4.
ISR 1, ISR 2, ISR 3, and ISR 4. And there will be all the methods will be used. Whenever there is, let's say there is interrupt from device 2, IR 2 will be served. Then in this case, microprocessor will jump where? ISR. And in case of IRQ4, microprocessor will jump to ISR. And before jumping to the subroutine, what microprocessor will do?
We push the program context.
It will push the program context. It will push the program context. What are different components of the program context?
Status register.
Working register, status register, and program. Okay, so it will push on the stack. Okay, now complication arises when there are multiple interrupt. So there are different priorities. Okay, now if two devices are serving an interrupt at the same time, what should microprocessor do? Priority. So now we have first priority, high priority. So highest priority device will be served first and lowest priority will be. So one mechanism is priority based. So it means that let's assume this IR1 has the highest priority, it is the highest priority and it is the lowest priority. It is the highest priority and it's the lowest priority. So which will be served first? IRQ2 will be served first and IRQ4 will be served later. But it may cause starvation. It may cause starvation. Why starvation? Now let's assume if these two devices are generating the interrupt again and again, generating an interrupt and again and again, and IRQ4 is also generating an interrupt, it will never be serviced.
Yes, sir.
Yes.
Okay, so it will serve as starvation. It may be unfair. It may be unfair to some of the other devices. So we also have another mechanism we call as rotating priority. In the rotating priority, now let's assume if we say that now we say we have priority Q. So it means IRQ1, Q2, Q3 and Q4. Which device has got the highest priority?
Q1.
Q1, because it's on the head of the queue. It has got the highest priority. When it's serviced, so then the priority queue is updated, then
Q2, Q3, Q4.
and Q1. Even if it's Q2, Q3, Q4 and Q1, if it is 0, it is 0, it is 1 and 0. Now which device will be served now?
Q2,
Q4.
Q4.
Why? Because Q2 is not generating an
Interrupt.
interrupt. When Q4 is serviced, what will be the priority queue?
Q2, Q3, Q1, Q4. Yes, sir.
Okay, so at first it will check because not only it's not necessary. It's not necessary that the request that is on the top of the queue will be serviced, because if it is not generated in interrupt now, so why should we serve it? Why should we serve it? It will be only served when there is
A request.
an interrupt from that corresponding device. So okay, this mechanism is called as rotating priority. So in your opinion, which mechanism is better?
Rotating priority.
Rotating priority is fair or unfair? It's fair. Okay. Now this in this mechanism, microprocessor always knows that okay, which device is generated in interrupt, and he knows that to which subroutine it will jump. Which subroutine it will jump. Okay, now what is the disadvantage of this approach of multiple interrupt lines? What is the disadvantage? What is the disadvantage of this approach?
क्यों maintain करोगे?
Q2. If there are multiple interrupts, doesn't matter Q maintain. The disadvantage of this device if there are many devices. Let's assume there are 256 devices, or let's assume 100 devices. How many pins do you need?
That amount 256 or
256 pins, so you need a lot number of pins. And maybe
Space was,
microprocessor is not like capable to handle all of this at the same time. So actually, it needs dedicated pins for the microcontroller or for the microprocessor. Okay, so now typically if you look at this device, so instead of using this, we have an intelligent device. We call it as an interrupt controller. And device talk to whom?
interrupt controller.
To interrupt controller. And who talks to the microprocessor?
Interrupt controller.
Interrupt controller. So it relieves the microprocessor of the burden. And it tells the microprocessor, and now the basic problem with this, which device to serve. So there are different mechanisms. I will explain this one by one. The first mechanism, we call it as software pool. And how it will now we have software pooling. So in this mechanism you have single IRQ and single I acknowledge. So now in this case there is some device controller and we have 4 interrupt requests: IRQ1, IRQ2, IRQ3 and IRQ4. So if any of these generated requests, so microprocessor is being notified, okay, that request is being generated. But microprocessor does not know who has generated an interrupt. Okay, now microprocessor acknowledge to this device controller, and this device controller will acknowledge, I acknowledge 1, I acknowledge 2, I acknowledge 3 and I acknowledge 4. Okay, I acknowledge 4. Okay, now in this kind of mechanism, there is one ISR, single ISR. There is a single ISR. So whenever there is an interrupt, it will jump to the ISR. Before jumping to ISR, what will happen?
वो context store हो जाएगा.
The context of the program should be pushed on the stack. So that will be done. So we are not going into that details. So in software pooling, there is an ISR. Then there is this is a general ISR that will be called on each of these interrupt subroutines. Then the microprocessor will ask each individual devices check, okay, whether you have generated interrupt, it will ask this. Okay, so now there is some map. For this mechanism, I will explain this with some example. Now, there is a memory map. If you remember memory, what is a memory map? What is memory map? Memory map contains some addresses and some data. So there is a map, and for this map, there is some card this is called as maybe. And for each device, there is a request available. So actually it will say maybe this is $3000, maybe $4000, maybe $5000. Okay, maybe at this address it will contain the status, the internet request IRQ1 and then IRQ2 and then IRQ3, the status of these devices. So when it jumps, so what my processor will do, it will ask if D1 has generated an interrupt, device D1 has generated, where it should jump? Jump to ISR1, else if D2, jump to where? ISR2, else if D3, jump to ISR3, else jump to ISR4, and then why? Now now this is a C code. Now if you look at the assembly code, so we can say move R3. We are storing in any working register. Move R3 $3000. Then it will compare R3 with 1.